All right, so this is the third lecture of a series on this idea of conditioning and stability. And part of what we talked about the first time was just trying to understand what conditioning of a problem means. And what we talked about the second time is a little bit around stability of algorithms. So can you come up with stable algorithms to compute the quantities of interest? And both these issues play a huge role in actually most of scientific computing, because what you ultimately need to do is to try as best you can to have well-conditioned problems. So those small perturbations in the problem don't lead to massive changes in your solution, right? And you want to set up algorithms that are also stable, so that actually, you know, the answers you can get are trusted answers versus the algorithm inherently producing something unstable. So what I thought I'd do today is actually walk through a specific problem, which is of a least square fitting type problem. And this least square fitting problem is going to come in the form of AX equal to B. And we're going to talk a little bit about how we actually compute conditioning on such a system. Okay, so and in particular, so we're going to condition on AX of, consider the conditioning of AX equal to B, and this is going to be a least squares problem, the way we set it up. Okay, so AX equal to B is what we want. I want to solve this. And we've already talked about solving this. This is going to be one of the, you know, it's the basic operation you have in linear algebra is AX equal to B, right? And in this case here, we're going to consider this to be an overdetermined system. Okay, so let's consider A, which is some matrix, which is m by n. And in particular, I want this to be such that m is bigger than n. So it's going to be a matrix that's rectangular. There's going to be more rows than columns. So in other words, more constraints than unknowns. That's the overdetermined part. B itself, of course, the vector, which is m by 1. And the solution x here is what I'm trying to discover or compute, and x itself will be an n by 1 vector. All right, so this is the problem setup. And in particular, because m is bigger than n, what this problem really looks like, generically, is something like this. So this is the sketch of the problem. This is the number of unknowns. Unknowns is here. This is the number of constraints here. So you see the number of constraints is bigger than the unknowns. So this is simply an overdetermined system. I can't remember if I said over or under, but this is overdetermined. And in general, for overdetermined system such as this, because I have more constraints than unknowns, I can't actually satisfy AX equal to B. So the second lecture of this course, what we talked about is the fact that when we go to solve AX equal to B, oftentimes we're solving, in many cases, systems that are over or underdetermined, sometimes massively so. And of course, there are cases where solving AX equal to B where A is square, but right now we're thinking about this as an overdetermined system. So what does it mean to produce a solution to something like this? We're going to make one more assumption, and that A is not only m bigger than n, that A is full rank. Okay? So in other words, the columns of A span, or span a space of n dimensions. So it's full rank. So there's no two columns that are the same or some scaling of the same. Okay? All right. So those are the assumptions we want to work on. And what we're going to really address here is thinking about conditioning of this least square problem. Okay. So first of all, let's talk about the solution to this. Since what we know we can't do, we can't actually satisfy this because there are more constraints than unknowns to satisfy this. What we're really going to do is think about solving this. And the reason the least squares comes up is because we're going to solve this in the least squares way, which is what we're going to actually do is find the following. We're going to find the x that minimizes b minus ax. In other words, just take the b to the other side or ax to the other side, right? So I can't make this satisfy this. What I'd really like to do is ax minus b to be 0, but if I can't do it, I like it, at least make it as small as possible. And so here is the optimization problem that we actually need to solve, right? B minus ax, find an x that minimizes this quantity. And this is the 2 norm between these 2 vectors, ax and b. Okay? So what are we trying to understand here? What we're trying to do now from the conditioning point of view is there's 2 quantities we want to actually produce. There's going to be a solution x and some approximation to b, sorry, this is supposed to be ax here. And y, which is an approximation to ax. So in other words, one way to think about this is that I want to minimize the vector b minus y. So I'm interested in these 2 quantities, y and x. In particular, when we come to conditioning, what we're very interested in a conditioning problem is to say, I'm given the a and the b. I want to understand if there's perturbations in a and b, how does it affect x and y? X is my solution. Y is my approximation, essentially, to satisfying this. Okay, those are the 2 things that you're actually kind of, in a sense, computing out of this process. So what we want to understand is, again, perturb these, ask what happens to those. Okay. So that is the statement of what we're going to go after here. So what I'm going to do is erase this picture. Need it. I'm going to draw another picture. And this other picture is going to start to frame for us what we want to think about doing with this. And in fact, one of the things that we want to start thinking about is when we look at this problem ax equal to b, one way to think about the solution to this is that, well, I'll write it here in a minute. I'm going to first draw this picture. Is that what we're looking at is in some coordinate system, okay? The matrix A has some range. And what I'll do is here is just envision what that range might be. So the range, let's say, of A is here. Okay? Now, remember, I have an overdetermined system, so this B, and remember that B itself is m-dimensional. The range spans an n-dimensional space. So whenever I project B onto this range, it doesn't have to live in the range itself, okay? It could be the case that B projects into the range, but generically, B sits outside. So there's some component of B that sits outside the range of A. So let's say that B is this vector here. So I have a point, B here, and the range of A is here. And this is generic because, again, it's overdetermined because B sits in an m-dimensional space, and my rank or span by range of A sits in an n-dimensional space, which is smaller. And so what I want to do is start thinking about, okay, what we've been talking about this whole time is this idea of projectors. And this is what we spent a lot of time talking about with the QR algorithm. in terms of building projectors, because that's how we did Gram-Schmidt orthogonalization. And so what we're going to say is, what is the projection of this B onto the range of A? Right? So that's going to be the vector y. And the vector y is A hitting X. Okay? So remember, it's AX equal to B. And if A hits X, then I'm going to live in this space here. Because remember, A has a range. And this now is going to say project X into a range of A, which is Y. And I want this Y to best approximate that B. That is the entire goal of what you're doing here with least square fitting. Okay? So another ways to write this is that this is the projection of B onto this range space. That's another way of saying it. That projector is take me onto this space. By the way, what is this vector here? This is the residual. It's given by here. It's just the difference in these two vectors. That's this vector right there. Okay? Okay, so this is the basic setup. This is, imagine this in higher dimensions, an m-dimensional space and n-dimensional space. Here I've only drawn it, in like basically a one-dimensional subspace is what the range of A is, and you put the B here, and this is the projection. But this should give you the cartoon of everything we want to be thinking about when it comes to these projections. Okay. So let's frame the conditioning of this problem. One other variable I want to call here is going to be this angle theta, and we'll bring that up in a moment. So here's what you're given. The data. You are given A and B. That's given to you. And A and B are here. What you know about A, it's full rank, it's m by n. What B is, m by 1. That's what you're given, that data. Your goal is to make a computation. And your goal to compute is X and Y. X is the solution, but what is Y? Y is A times X, which is your approximation to B, remember? So A times X is some Y. So I can't actually reach B. B sits in some higher dimensional space. So I'm looking at the difference between Y and B, which is right there. This is it. In other words, Y has to live in the range of A. B doesn't. Okay? B is higher dimensional. It's m-dimensional. Y is n-dimensional. But here's the relationship between Y and B, right there. Y lives in the range, B is outside the range, and then you can see that I want to minimize the difference between Y and B in my solution. When I compute this X, somehow I want to minimize that. Okay? So more broadly, the way to think about this is given this data, and these are the answers I compute, I want to understand if I perturb the A or the B, how much does it change the X and the Y? That's what I'm asking in this. That's the whole idea of conditioning, right? Conditioning is about if I make small changes here and small changes here occur, then it's well conditioned. If I make small changes here and big changes happen in the solution, it's ill conditioned. And it's very important you know when your problem is ill conditioned, because you're going to get wildly different answers for the smallest changes here. And those are exactly the kind of problems you want to avoid. Computationally, in other words, you can't necessarily trust the answer of an ill-conditioned problem. Okay. This starts to frame for us in a very concrete manner of AX equal to B, how to start thinking about conditioning. This is a really important graphic. It's important that you understand this, right? I'm just simply talking about AX equal to B, which we all think we know how to solve. But now we're looking at it from the point of view of an overdetermined system. And you can do things like this for underdetermined, whatever you want to do. You can start playing around with what does the conditioning of matrices like this look like for the overdetermined system. That matrix A hits X, it lives in a range. The B can be outside of the range. And I want this Y and B to be close. And that's going to make AX minus B be close. And I want this in a least square sense. In other words, an L2 norm. So there's going to be some quantities I define here that are going to start setting up the conditioning for us. One, we've already talked about the condition number of a matrix. And we had already written this down previously. But the condition number of a matrix is the norm of the matrix for an overdetermined system times the pseudo inverse of the matrix. And the pseudo inverse is gotten by least square fitting. Okay, so you try to solve the inverse problem, in other words, the inverse problem, and you do it through least square fitting. And that's what this object is. It's called a Moore-Penrose pseudo inverse. And that is the definition of the condition number for an overdetermined system, which, by the way, simply comes down to the ratio of the singular values of the matrix A. So if you do an SVD on this matrix, you determine the highest, biggest singular value, and then use sigma n, which is the smallest singular value. That's the condition number of that matrix. You get worried when this is really big, right? Like if this is 10 to the 10 and higher, 10 to the 10 to 10 to the 16, this is very poorly conditioned. If the number here is like 100, 10, 5, you're fine. But it's when it's up 10 to the 10 and higher, you have to worry about what your solution is going to look like in working with this matrix A, because this matrix is ill-conditioned by nature. Okay, so the SVD serves this nice purpose of being able to produce for us condition numbers. All you got to do, SVD is guaranteed to occur for any matrix. You look at the singular values, biggest, smallest, divide them, condition numbers there. There's another quantity we want to look at, which is this angle theta. What you'd really like to do, obviously, is make theta to be small. So theta itself, compute this, is just the inverse cosine of y over b. Okay? That's what cosine is. And of course, if b and y are the same, this is great. Theta is going to be 0 because this is 1. Okay? That's ideal, but of course, that's assuming that b actually lives in the range of a. And generically, since this is m-dimensional and your solution's n-dimensional, that doesn't have to be the case, right? B lives in a higher dimensional space, has more freedom in some sense. And so this is the projection down onto the range of A, which is full rank. This is the n-dimensional space, and this is some m-dimensional space. If it happens to be that B lives in that range, great. This will be 0. The angle will be 0. But generically, it's not 0. This is some measure, and you want theta to be as small as possible, right? That's one way to think about it. One further quantity we'll define, eta. And this is going to be the ratio of AX over Y. So this is going to be the matrix norm, the norm of the solution divided by Y, which is A times X, right? Which is this. It's your approximation to B. So in other words, one way to think about this is you're doing AX equals B, and you're computing essentially the ratio of this side versus this side here. And by the way, right, B is a y. That's what you're really computing, is something like this, okay? Or actually, b is like, sorry, y itself, sorry, I meant to put y here. Y is your computation of this. So y is your approximation to b. So this is sort of, in some sense, you look at this, you divide by b, but b is going to be approximated by y. So you're kind of interested in what happens to this ratio, and that's going to be eta, okay? And I can replace this with y. Y is a times x itself. That's another way to look at it. Okay. So 3 quantities: kappa, which is the condition number; theta, which is the angle between, in other words, it's the angle out of that higher dimensional space. You get to, this has a range, you get to pick y, you get to think about your solution and how you construct your solution so that this y and this b are, in some sense, as close as possible. That's the whole goal in the least square fit, is to say, I have a solution x that I want to pick such that y and b are as close as possible. And then eta, which is in some sense the ratio of your, what I said, just x, it's really evaluating x over b. And you want to ask the question, what happens to these quantities? Because these are going to all be metrics of performance. That's the one way I think about this, is that these will show up in all the conditioning problems we look at related to this ax equal to b for overdetermined system. A couple more comments about these quantities. Kappa itself, maybe I should erase some things. Okay, actually, I'll put it here. So theta takes on values between 0 and pi over 2. So what I want to start talking about is, what kind of values does it take on? This comes from 0 to pi over 2. In other words, you could maybe find a solution where y and b are aligned. In other words, if it's 0, that means b was exactly in the range of a. Okay, that's what 0 means. In other words, b and y sit in the same subspace, the range of a. What pi over 2? Pi over 2 means that b is exactly orthogonal to the range of a. In other words, there is no projection of b onto the range of a. It's orthogonal. Remember, b lives in an m-dimensional space, x lives in an n-dimensional space, so you can definitely pick a b that is orthogonal to the range of a. Okay, so that's what the pi over 2 is. So those are the values that you can take on for theta. Kappa, which is the condition number, goes anywhere between 1 to infinity. Well, okay, infinity doesn't really exist in your computer, right? But infinity here, what we mean by infinity is like 10 to the 16. Okay? All right, but in theory, it can go to infinity if you're really dividing by a 0 here. In other words, if it's not full, if the matrix itself is not full rank and your sigma n is 0, then the condition number theoretically would be infinity. But when you actually compute these things, because of numerical double precision numbers, it's like 10 to the 16. And it reflects the fact that we have 16 decimal place accuracy. But it can go from 1 all the way up to 10 to the 16. And finally, this eta value here goes from 1 all the way up to the condition number of a. So that's its range of values. Okay, so if the condition number is big, this can get really big. If the condition number is small, then this could be all the way to 1. If the condition number is 1, then this is 1. Okay? All right, these are the quantities we want to start considering here in evaluating the conditioning of this problem. And now we're going to start thinking about a little bit is how do we start computing some of these condition numbers? Okay. All right, I'm going to erase this because the board's getting a little choppy here. And all right. So I'm going to erase this, although hopefully you've stored that in your memory banks, because that is the picture that tells 1,000 words. And what I want to do is now write down a theorem. And this theorem is right out of Trefethen's book, so you can look at it, and it's really investigates essentially the conditioning problem for this least square fitting. Okay, and it addresses the issue of if I perturb the data B and A, what is the impact on the solution X and Y? That's what we want to address in conditioning. Okay. So here's your theorem. So if A is some m by n, so m is bigger than n, and it's full rank, and B is m by 1, the least square problem has the following, has the sensitivities or conditioning from AB to XY. Okay, so in other words, that's your data, perturbations here, how do they affect your XY? So the way he puts this together is actually kind of nice, kind of clever, which is I'm going to look at my outputs, which are X and Y, as a function of my inputs, which are B and A. And so what I want to start to understand is if I perturb these two, what is the impact on these two? And I'm going to make a little graph here, and I'm going to show you how we get some of this, or a little table. Let me write these first, and then we'll discuss. These are things that can be worked out either explicitly, the first two, or by bounds, which are the second two. But what it tells you is essentially a map between the perturbation and how that perturbation of B affects Y, or the perturbation of B affects X in a conditioning sense, or how the perturbation of A affects Y, how the perturbation of A affects X. So you can work all of this out explicitly in terms of the dependencies of these key quantities here, which are the condition number of the matrix, theta, which is the angle between B and your projection of B onto the range of A, and eta, which is this essentially ratio of norms of A and X and Y. Okay, so this table here is exactly this theorem, which tells you if you have these conditions, here are the condition numbers relative to these perturbations. So let me be a little more explicit by what I mean by the condition numbers of these perturbations. So one can think about this one here, for instance. In fact, this is a table of 4 things. So remember, condition number is something that we often think about for matrices, but the conditioning of a problem is a generic idea. So in other words, it doesn't have to be a matrix. It is the condition number of a problem is about perturbations of the problem. How do they relate to the outcome? So here what we're going to compute in this 4x4, they're something like this. The perturbations, in other words, the condition number, kappa, as respect to how B, perturbations in B influence the value of Y. The perturbations of kappa in terms of B and how it influences X. So when I perturb B, I ask how it affects Y, and Y, remember, is A times X. So I want to, that's my approximation to the vector B. How much does it affect my approximation to the vector B when I perturb B, the data itself? How much is it, if I perturb B, does it affect my solution X? Remember, X is different than Y. X is my solution, Y is my approximation to B, which is A times X. We also have these two quantities, which is how does the condition number get affected? Mapping A to X. Okay, so in other words, if I perturb the matrix A, how does it affect the outcome Y? That's here. If I perturb the matrix A, how does it affect my answer X? That's here. So the nice thing is I've already given you the answers. And so right away, if you want to know what's the condition number of that solution, so if, for instance, if I perturb B, the right-hand side of AX equal to B, I perturb this guy, then I can ask the question, how much, what's the condition number of that to my solution? It's given right by here. Look at it, it's got the condition number of A divided by this angle theta and eta. And of course, if A itself has a high condition number, then this is going to have a high condition number as well. Versus here, if I just ask how does it perturb Y, in other words, my approximation to B, it goes like 1 over cosine theta. So this doesn't necessarily mean it gets big or small. Okay? All right, so how do we actually compute these? Because this is what they are trying to represent. These are the kind of things we ask about in conditioning. And it's really important when you set up an algorithm that you try to set them up to be well conditioned. The reason numerical analysis has books and books and books and books written about how to compute things is because of these issues. It's not just because people had nothing better to do and we're just, okay, maybe some of it's that too, right? I mean, like we like to solve problems, right? In math, like even if just for fun. But in this case, when you go solve real problems in the sciences, oftentimes, you know, the first attempts we had at solving those problems, oftentimes these problems led to ill-conditioned problems that we needed to fix. We needed to find a way to make these so that they're not big, so that the condition numbers are okay for the problem. So when you get a solution, you can trust it. Okay? All right, so that's the theorem, and those are the results that we're trying to get out of it. So how do we show some of this? So what I'm going to focus on for this lecture is just these two results. If you go to Trefethen, you can find his calculations for these. So I'm going to focus here on if I perturb B, what happens to Y, what happens to X? How do I evaluate that? And that's what we're going to do here. And then in some sense, if you want to read more about conditioning and stability, there's quite a bit more in Trefethen that you can follow up on. But we're going to move on to other topics as we move forward in the class. Okay, so let me erase this theorem and let's start talking about how I would produce some of these results. Because at the end of the day, if you really want to do some numerical analysis, and this course is about an introduction to numerical analysis, it's important that you actually compute these things for an algorithm or a scheme or a structure like this, a decomposition such as this, so that you know and have some confidence about how good are my solutions. Are they well conditioned or not? Are they well posed or not? So these they're more than trivial things. They are absolutely critical. So for those first two rows that we want to show, we're going to start off with one of our big tools, the SVD. we're going to say that the matrix A itself, right, has an SVD. Now, this is guaranteed for any matrix. I have an SVD. That's its form. Two unitary matrices, diagonal. So that's the generic decomposition. Now, what I'm going to ask is, what happens when you perturb the data itself, A? Well, if you perturb this, recall that these two matrices are unitary, so they always just have unit norm. So in some sense, they might change their rotations a little bit, but their norm is just 1. So all of the perturbation is actually going to get taken up in this sigma matrix. So if you perturb this, it's going to mess around with the singular values. These are just unitary operators on either side. Okay? So in other words, perturb A, and that singular matrix is what, this singular value matrix, which is the diagonal here, that's what actually fields it. In other words, that's what gets changed here. Perturbations here get transferred directly here. These are just unitary operators. Their norm is still 1. So one way to think about this, roughly, and I'm just going to do this, is just say, all right, let's assume for a moment A is just a sigma. So we're going to ignore the U and V for a moment, okay? Because this is going to illustrate the entire point for us. So the point about this is, remember that A itself is a, not necessarily tall, skinny, but that's the way it goes, right? There's more rows than columns. So this thing here, under diagonalization, is going to be sigma 1, sigma 2, all the way down to sigma n. Zeros below and on the off diagonals. Okay, that's the structure of that matrix. Or another way to say it, this is equal to, in the broader sense, some A1 divided by 0. So wherever these zeros are, that's what we have here. 0, zeros, and then this is some upper structure there. So this is really canonical, because even if I don't have this, even if this wasn't exactly sigma, this is really the structure of what I have to look like in the A matrix. There's a bunch of columns, rows down here that I don't have to, that are just basically silent, as it were. So let B be two parts, B1, B2. Under this diagonalization process, okay, then Y itself, which is my projection. Remember, Y was you take your vector B and you project it onto the range of A. That's what Y was. That was my approximation of what B was onto the range of the matrix A, which I can write as the projector of B, where this thing here is the projector onto the range of A. Okay? But this thing sort of looks like this. Here it is. Look at that. It's got a bunch of zeros and it's got A1 up there. So really what this is going to see is it's going to just zero out all those B2 terms. And so Y itself in this diagonal coordinate system that we've been working with here, SVD, is going to look something like this. Doesn't care about this B2 stuff. Okay, so one way to think about it is I'm projecting into the n-dimensional space, which is the range of A, and from n+1 to m dimensions, they're outside of the range. And so when I do this projection can't reach these things. So when it projects, those are all zeros for it. That's what it's doing for Y. It's saying, I don't know what those are all 0. I span an n-dimensional subspace. Okay, so that's kind of a generic construct that we want to come up with. And you'll see how this plays out in terms of our approximations to those condition numbers. So let's talk about X. So now I've got it into this space that I'm going to work with. So what about the solution? Well, now what I have, I've decomposed this matrix A into this. So really what I have is A1 and zeros acting on X is equal to B1 and 0. So now what I have here is everything is constrained to this n by n subspace whose solution is X is equal to A inverse, A1 inverse, times B1. So in other words, this is the solution because in this space, this thing is non-singular. This spans, remember, we made the assumption that A was full rank. So this is now, I've moved into a new space by the SVD where this holds. There's the solution. It's the inverse of acting on B1. Okay. The projector itself, P, looks like the following. It's this identity. So it's some n by n block here, which hits this thing and projects onto that n by n subspace. And there's the solution of it. Okay, so this is all setting up a preliminary, and it's really setting it up in the context, if you notice, in terms of projectors. Remember, everything ultimately is going to be about projectors because everything we're going to do in this linear algebra course is about putting it in some subspaces or some lower dimensional spaces often, and we got to project into these subspaces. And so all I've done here is when I've solved this overdetermined problem is found this n by n subspace that we're going to actually go work on. Okay. All right. So this is setting up the preliminaries. So X here is the inverse acting on some subspace of the B1. Okay. There's an n-dimensional subspace that's of interest to us. The rest of it is outside of the range of A. So what I've done is set up the problem into stuff that's in the range of A, stuff that's outside of the range of A. That's the way to think about this. Okay? All right. Let me erase this and we'll keep going. So with that formalism, what it allows us to do is to start to ask the question of computing the condition number of, for instance, X and Y as a function of perturbations to B itself. Okay, so remember that Y itself is the projector acting on B. In other words, take this projector, I had just written it down there, take the projector, hit it on B, that's going to get me into the Y, and Y is in the range of A. Now remember that a projector is unitary, so I have that. And so if you remember the definition of, here we go, I'm going to just do this. So now I ask the following question. What is the condition number, perturbations of B going to Y? So the definition of that basically is given right by here. I have, this is the problem I'm trying to solve. And so you have this. So basically divide by here, take the ratio. This is the ratio of essentially these two sides of the equations. So this is given by here. So I just take this, divide by Y, and then I take the norm of the ratio. This is what I have. But what's P? That's the projector. The norm of it is 1. So because P is a unitary operator, I just have this. And this was exactly the definition of the cosine of the angle of theta. So this comes out to be 1 over cosine theta. So that the theta was one of the angles that I defined before. So there you go. This is the condition number of B acting on Y, and it's 1 over cosine theta. So you can compute it explicitly. Okay? That's what it means to have this condition number. small changes here over here, like, right? That's what we're looking for. If I change this a little bit, what happens to changes here? And now you can compute it explicitly. So this is the condition number of what's happening to y as I perturb b. And I can write down an explicit representation. Okay? So that was the top left of my table. Let's go to the top right, which is I want to now compute the condition number b. How this changes perturbations in b affect x. Now what we know is we're going to approximate x by this guy here, the pseudo inverse of a acting on b. That's the least square fit. And so if we start computing this, we say, okay, I'm going to try to solve that problem, which is going to lead to the same kind of thing we have here. It's the ratio, which is a pseudo inverse over x over b. Same thing I did here. Just basically divide by y. I took the b underneath. So that's the ratio. Same thing here. That's what we're going to assume, is that that pseudo inverse is my approximation. That's the least square solution to this problem, right? That's what we're doing here. So I get this here, and now I ask the question, all right, so what does this mean? Well, one thing you can do with this is I'm going to multiply top and bottom here by the solution y. So what you're going to do is you're going to get out the following pseudo inverse. Then you got b over y, y over x. Now the reason I wanted to do this is because this here, so this here turns out to be 1 over cosine theta. This here turns out to be the norm of a divided by eta. And so if you have the norm of a times norm of a pseudo inverse, that is the condition number of the matrix A. Okay, this is 1 over cosine theta, and there's an eta here, which goes to our definition. The point is, if you look at it's pretty simple algebra to just simply show that what this turns out to be is the following. That quantity there. Remember, I defined those 3 quantities, which was the condition number of the matrix A, the angle theta, which is the angle between where B lives and its projection to the range of A, and then eta, which was another quantity we defined, which was the ratio of some norms of AX over B. And so what here you have is an explicit computation now of what happens if you perturb the B and what happens to the solution X. Is it well conditioned or not? You can compute that number. And when you compute that number, you ask, is it big or is it small? If this number is really big, you know that this is an ill-conditioned problem. It's not, in some sense, not well posed. So your answers can vary wildly by small changes to B. However, if this number here is order 1, so in other words, I make changes to B, X changes by a small amount as well. So these are ways you can explicitly compute the conditioning for this problem here. And of course, you can do the bottom row as well. I'll let you follow up on Trefethen's book if you'd like to follow up on that. And this just simply gives you an idea of how you might approach some of these problems and the conditioning that goes with them, right? You want to set up well-conditioned problems. And if it's ill-conditioned, the goal is to figure out, can I rewrite it? Can I come up with a different algorithm? Can I make some approximations to compute it differently so that all of this is well-conditioned? If it's not well-conditioned, small changes in A and B are going to lead to large changes in your solution or your approximation to B. And that's problematic when you do scientific computing. So I'm going to stop there.